Every year, the world produces over 10,000 tons of titanium discs, the material used to create the hearts of airplanes, implants for surgeries, and even parts for spacecraft. A single disc can weigh more than a smart car, but it fears neither temperatures of 1,800 degrees Fahrenheit nor the vacuum of space. How does a gleaming superdisk, capable of withstanding thousands of revolutions per minute, emerge from a gray, spongy mass? What do aviation, medicine, and the titanium hell of furnaces have in common? This isn't just manufacturing. It's a show of strength, precision, and engineering magic. Let's dive into a world where metal takes on its perfect form. Titanium discs are blanks shaped like thick discs made from titanium or its alloys. They serve as the starting material for parts in highly critical fields: aviation, medicine, space, energy, and automotive manufacturing. Titanium is a true superhero among metals. It's lightweight yet extremely strong, withstands insane temperatures, resists corrosion, and doesn't react with the human body. That's why it's used for everything, from aircraft components to implants. But pure titanium is a bit finicky. It's difficult to machine and can be brittle under certain conditions. Therefore, it's often mixed with other elements, creating alloys. The most popular alloy consists of titanium with 6% aluminum and 4% vanadium. It's strong, wear-resistant, and easier to form. Aluminum adds lightness and heat resistance, while vanadium adds flexibility. For medical devices, pure titanium or alloys without toxic elements are used. Depending on the task, titanium can be harder, more ductile, or more resistant to extreme conditions. That's why manufacturers choose not just titanium, but the specific alloy that perfectly meets the particular challenge. Titanium for discs comes from titanium sponge, the primary raw material extracted from ores, mainly ilmenite and rutile. The largest deposits of these ores are found in Australia, South Africa, China, Kazakhstan, and Canada. But the sponge itself is produced where complex manufacturing facilities exist because the process of converting ore into metal is very energy intensive. It all begins with a dirty grey, pumice-like substance, titanium sponge. It arrives at the plant in large containers and bears almost no resemblance to the future aerodynamic part. But this is where the journey starts, ending with the gleam of a perfectly polished disc capable of withstanding thousands of revolutions per minute. First, it's checked for impurities and moisture. Acids or solutions that react with impurities are used, removing them from the titanium surface. This process might involve treating the raw material in special baths. Titanium parts might also undergo abrasive treatment, such as grinding or sandblasting, to remove surface contaminants. After cleaning, the titanium raw material undergoes heat treatment to improve its structure. The raw material is heated to a specific temperature, usually between 1,300 and 1,600 degrees Fahrenheit, and held there for a defined period. This helps reduce internal stresses that might have occurred during previous processing stages. If necessary, the raw material can be heated to higher temperatures to achieve homogeneity in the alloy structure. This ensures an even distribution of elements within the material, enhancing its strength. After heat treatment, the titanium undergoes a fascinating rapid cooling stage, which is quite a spectacle. When the metal is removed from the furnace, it glows with bright shades of red and orange, reflecting the high temperature it was heated to. Cooling can be done in several ways, by quenching in water or by air cooling. When submerged in water, you can observe the hot titanium creating foam and bubbles as it rapidly contacts the liquid, emitting a characteristic crackling sound. This is visually impressive, as the boiling water witnesses an incredible transformation, from a potentially malleable state to a strong metal. Alternatively, air cooling is calmer, but no less captivating. The metal gradually loses heat, changing its color and texture. This process, although less dramatic, demonstrates the smoothness and elegance of titanium's transition to its final form. Then, the material is loaded into special crushers or hammer mills. The main purpose of crushing is to reduce the particle size of the titanium, facilitating further processing and ensuring material uniformity. The crushed particles can be used in various processes, such as producing powder alloys or forming new parts. After crushing, the resulting particles may be washed to remove residual debris or impurities. They are then dried in preparation for further processing. To manufacture the titanium discs themselves, the blanks are heated to high temperatures, typically up to 1,500 or even 1,800 degrees Fahrenheit. This is done to make the titanium softer and easier to work with. The heated blank is placed in a press or hammer. Impact action or pressure shapes the blank into the desired disc form. During this process, the titanium undergoes significant deformation, leading to changes in its structure. For casting, however, special molds are made, usually from steel or cast iron. The molds must be very precise to ensure the correct geometry of the disc. The titanium is heated until it turns into a liquid. This is usually done in vacuum furnaces to prevent oxidation. The liquid titanium is poured into the prepared mold. After cooling, it solidifies, taking the shape of the disc. Casting allows for the production of discs with complex shapes that are difficult to achieve by forging. Now it's time for machining. Before machining, the discs are cleaned of dirt and residues. For this, they are immersed in a special bath with a solution that removes slag and grime. The water foams up, and the disc becomes clean. Next, the discs are secured on lathes for stability during machining. A lathe is used to remove material from the edges of the disc, achieving the required diameter. Thin metal shavings curl away from the cutting tool like a slender snake. The contours and profiles of the disc are formed according to technical specifications. If grooves or holes are needed, a milling machine is used. Then, the discs are processed by grinding machines to achieve the smoothest possible surface. This is important for reducing friction. Finally, they are polished to obtain a shiny surface, which also enhances their aesthetic qualities. Polishing can further protect the disc from corrosion. After polishing, the surface becomes smooth, reducing the likelihood of dirt and moisture accumulation. Fewer imperfections and cracks mean fewer chances for corrosion. Polishing also seals microscopic pores that can retain moisture and contaminants. This significantly reduces the risk of oxidation. Afterward, the disc is inspected for scratches, cracks, or other visible defects. Calipers and micrometers are used for precise measurements of the disc's diameter and thickness. To detect internal defects not visible on the surface, ultrasonic testing is performed. This inspection method does not require direct contact with the disc. A special transducer emits ultrasonic waves into the disc material. As the waves travel through the disc, they reflect off boundaries such as defects or the material itself. The time it takes for the waves to return to the transducer is measured. This allows for the detection and sizing of defects. Specialized software analyzes the received data, providing information about the disc's condition. This is a very fast process, allowing many discs to be checked quickly. Titanium is 40 times lighter than steel, but has comparable strength, making it ideal for the aviation and automotive industries. It does not rust or corrode in most environments, making it a durable choice for various applications. In the United States, an average of 10,000 to 15,000 tons of titanium is produced annually. A significant portion of this amount is used for manufacturing discs and other components. Thus, on a monthly basis, this could amount to 800 to 1,200 tons of titanium discs. Leading companies in the United States, such as Boeing and Lockheed Martin, actively invest in the production of titanium discs to meet the needs of their programs. It is expected that in the coming years, the demand for titanium discs for aviation will grow by 5 to 7% annually, especially considering new technologies and increased aircraft production. What if I told you that every bottle you throw away could live an infinite number of lives? Ardagh Group creates more than 160 million packaging units each year, using thousands of tons of recycled glass. Now imagine the scale: industrial crushers that process up to 3 tons of glass per hour, and furnaces working at full capacity to give this material a new life. What does this grand transformation look like? Keep watching. You will be amazed. The company participates in various programs aimed at reducing landfill waste, actively collaborating with municipalities and other organizations to collect and recycle glass. Through these efforts, ARDA increases the proportion of cullet used in production, as reusing glass is more energy efficient than making new glass from raw materials. For example, the company supports deposit packaging systems, where consumers return used glass bottles for recycling. They also work with waste sorting centers, providing equipment to clean and prepare cullet for processing. In many countries, ARDA funds community education programs to raise awareness about the importance of recycling glass. Through these initiatives, ARDA Group not only minimizes landfill waste, but also significantly reduces production energy costs, as glass made from cullet melts at lower temperatures. This is an essential part of their sustainability strategy, focused on conserving natural resources and reducing environmental impact. Each year, the company produces over 160 million packaging units, highlighting its scale and importance in the global market. Thanks to advanced technologies and high manufacturing standards, ARDA Group remains an industry leader, contributing to economic development and environmental responsibility. The story of ARDA Group began in 1932 in Dublin, Ireland, when the company started as a small glass packaging manufacturer. Its founders aimed to meet the growing demand for glass bottles, driven by the expanding food and beverage industries. In its early years, the company produced bottles for local breweries and dairy businesses, gradually increasing its scale. A pivotal moment came with the strategic decision to expand through acquisitions. In the 1990s, the company began acquiring plants specializing in glass containers across Europe and beyond. It later entered the metal packaging sector, diversifying its business and tapping into new markets. Today, ARDA Group is a global leader in packaging production. Its growth story is one of transforming from a small regional manufacturer into a world-renowned corporation that remains committed to its mission, creating high-quality, sustainable packaging that meets the needs of the modern world. ARDA Group embraced the use of recycled glass as part of its commitment to addressing contemporary environmental challenges and economic trends. Glass is an ideal material for reuse, as it can be recycled an infinite number of times without losing quality. Over time, the company realized that transitioning to more sustainable production practices was not only an ethical necessity, but also a powerful business strategy. Several factors influenced this decision. First, growing demand from customers seeking eco-friendly packaging. In a world where more people are concerned about climate change and pollution, glass containers made from recycled materials have become an attractive solution for many brands. Second, economic benefits. Using recycled glass reduces energy costs. Melting cullet requires 30% less energy than producing new glass. This, in turn, lowers carbon emissions. Thus, using recycled glass has become a key part of their business, supported by both environmental and economic advantages. Garbage trucks deliver collected glass to specialized recycling facilities. There, it is first inspected to sort out materials unsuitable for recycling, such as ceramics, plastic, or metal. Next, the glass is crushed into cullet, small pieces that are easier to melt and clean. This cullet is then transported to glass manufacturing plants, where it is used as raw material for producing new bottles, jars, or other glass containers. The glass arriving at the recycling plant is initially inspected and sorted. Automated systems or manual processes remove foreign materials, plastic, metal, paper, or ceramics, that could disrupt further processing. The company employs approximately 20,000 workers globally. Before crushing, the glass is washed. Powerful systems rinse away dirt, labels, and product residues. High-pressure water jets remove everything: dried ketchup, wine remnants, stuck on labels, and even tiny bits of paper that seem impossible to clean off. This step is crucial for ensuring the purity of the raw material. Water streams splash everywhere as the glass passes through special brushes and rollers spinning at high speed, polishing each piece to a shine. The noise resembles a small waterfall storm. Watching clean, perfectly shiny glass emerge from the machines is a spectacle, transforming what was once dirty and labeled into something pristine. It feels like magic, but it is actually cutting-edge technology at its best. The cleaned glass moves into specialized crushers. There, it is ground into small particles using powerful mechanical hammers or rollers, resulting in fragments ranging from a few millimeters to several centimeters. This material, known as cullet, resembles gravel. Industrial hammer crushers can process up to 3 tons of material per hour. To remove any remaining foreign materials, the cullet passes through magnetic separators for metals and air jets for plastic and paper. Additionally, laser or optical scanners automatically sort the glass by color into clear, green, and amber categories. Sorting glass by color is not merely an aesthetic choice, but a critical technological process with several practical benefits. Colors affect the final quality and properties of the new product. For instance, clear glass is used for beverage or cosmetic bottles and must be kept as pure as possible. Green or amber glass, on the other hand, is ideal for packaging that protects contents from ultraviolet light, such as beer or wine. Color sorting is also essential for melting, as each glass type has unique temperature and chemical characteristics. Mixing colors can destabilize the process and risk producing defective batches. Mixed colors are harder to recycle. Such glass is often sent to lower priority uses or not reused at all, increasing waste. Properly sorted glass reduces energy consumption during recycling, as there is no need to clean the material of color impurities. Therefore, color sorting not only ensures the purity and quality of new glass, but also significantly reduces energy costs and maximizes the use of recycled resources. The finished cullet is stored in bins or bags and transported to glass manufacturing plants. Depending on the requirements, it is used as raw material for producing new glass. Though cullet appears sharp, storing it in bags is entirely feasible due to specialized materials. These bags, called big bags or flexible intermediate bulk container, are made of ultra-durable polypropylene with multiple layers that prevent tearing, even from sharp glass edges. Sometimes, the inner layer of big bags is additionally coated with laminated material for extra strength and dust resistance. The cullet, reduced to pieces ranging from a few millimeters to several centimeters, has edges that are less likely to puncture the bag material. Storing in such big bags is not only safe, but also highly convenient. The bags are easy to transport, stack, and dose for further use in furnaces. After preparation, the cullet is transported to RDOG Group factories, where it is transformed into new glass products. A significant portion of the cullet is loaded onto trucks, either standard or specialized, depending on the volume and route. For larger shipments, even rail cars are used to cut transport costs and reduce the carbon footprint. Upon arrival at the factory, the cullet undergoes another inspection. This ensures that the material meets all requirements, such as the absence of any foreign impurities or pieces of the wrong color. Afterward, it is fed into melting furnaces, advancing the recycling process to the next level. Incidentally, the closer recycling plants are to manufacturing facilities, the more economically and environmentally efficient the entire chain operates. This is another reason why RDOG Group actively supports local glass collection and recycling systems. Do you know what can amaze you even more than the flight of an airplane itself? It's life after the sky. Every year, thousands of airplanes are retired worldwide, and some of them become a source of metal for new automobiles or even construction frameworks. One single Boeing 747 contains around 165,000 pounds of aluminum, which can become the future raw material for dozens of other airplanes. Are you curious to learn how engines, which can cost up to $30 million, get a second lease on life? Or how first-class seats turn into part of a home movie theater setup? Are you ready to journey into a realm where technology, ecology, and business converge in one enormous hangar? Let us take off and explore. The first step in a retired airplane's journey is what insiders often call its removal from flight. In fact, this phase is sometimes referred to rather poetically as heading into retirement. Airplanes are retired when they reach a certain age, a certain number of flights, a certain tally of hours in the air, or when they simply become economically unviable to operate. Passenger airplanes typically serve from about 20 years to about 30 years. The metal gradually becomes fatigued from the repeated cycles of takeoff and landing, alongside the persistent air pressure at cruising altitudes. Engineers may detect micro-cracks or other structural issues, making further flights risky. Older airplanes require more frequent maintenance, which becomes expensive. Eventually, the costs of upkeep can overshadow any profit from keeping that aircraft in service. More modern airplanes consume less fuel, are cleaner for the environment, and cost less to operate. For instance, contemporary designs, such as the Boeing 787 or the Airbus A350, are far more efficient than older airplanes like the Boeing 747. International safety standards also keep shifting. If an airplane does not meet new standards and modifications prove too pricey, that airplane is retired. Occasionally, airlines retire airplanes because travel demand declines. During the coronavirus disease 19 pandemic, many older airplanes were retired ahead of their original timelines. Interestingly enough, cargo airplanes can keep flying for a longer period as there are fewer requirements for passenger comfort, and their overall load can be lighter. Yet sooner or later, even cargo airplanes head into retirement. Once an airplane is ready for disassembly, it is towed to a specialized hangar, where its second chapter really begins. The first priority is the engines. They are, beyond any doubt, the most valuable part. Engineers remove them first, perform detailed inspections, and then either overhaul them for reuse or break them down for spare parts. One of the staff members told me that a single engine can be more expensive than the entire airplane. Can you imagine that? The process starts with engineers reviewing the documentation for both the airplane and the engine. They want to know its overall condition, its servicing history, and whether any special precautions are needed. All fuel, hydraulic fluid, and lubrication systems in the engine are de-energized, with every liquid drained. This step is crucial, since even small amounts of leftover fuel or oil can be a fire hazard. The engine is linked to the airplane by dozens of cables, pipes, and mechanical connections. One at a time, engineers disconnect the electronics, hydraulic lines, and ventilation and cooling systems. All connectors are labeled so that they can be quickly identified whenever the engine is inspected or installed on a different airplane. The cowling is the protective shell around the engine. It is taken off to reach the main components underneath. This cowling is removed very carefully and often sent away on its own for inspection or repair. Engines can weigh several thousand pounds, so they must be firmly supported before removal. Specialized lifting platforms or cranes are used to ensure the engine remains undamaged during detachment. Engines are attached to the wing or fuselage by pylons, which are special mounting structures. Engineers gradually remove these attachments, frequently by hand, using high-precision tools. It is a delicate moment, since a slip can cause damage. Following removal, the engine travels to a service facility for inspection, repairs, or further disassembly. It is secured in a dedicated container that safeguards every part during transport. The engine is the priciest piece of the airplane. Depending on the particular model, it may cost anywhere between $10 million and $30 million. As a result, the removal process is carried out with extreme caution. Often, an engine is not taken off because of a failure, but rather to undergo planned maintenance, or so it can be installed on another airplane. In many cases, engines embark on a new life after refurbishment and upgrades. This underscores yet again that aviation is not just about flying, but also about pragmatic reuse and a certain technological artistry. The next thing that amazed me was the fuselage. The aluminum body of an airplane is not simply chopped into random pieces. Instead, it is sorted, cleaned, and directed toward recycling. This metal can be reborn as part of new airplanes, car parts, or even building materials. By the way, have you ever wondered how much aluminum is inside a single Boeing 747? It is about 165,000 pounds, which is impressive to envision. That quantity could practically spawn an entire fleet of future airplanes. Seats, which we usually see as nothing more than comfortable chairs for our flight, can also be reincarnated. They are repaired and sold to airlines that have tighter budgets. Sometimes they even end up with private buyers. Did you know that first-class seats can be purchased for a home movie theater? That idea is definitely on my personal wish list. Aviation electronics form another treasure trove. Every component, from onboard computers to navigation systems, is extracted and carefully evaluated. These parts often see further use in pilot training simulators or get integrated into other airplanes. Even seemingly small items, such as life vests, seatbelts, or tableware, find new owners. Some of them are turned into unique souvenirs. Do you recall those movies in which people collect aviation memorabilia? That is actually based on reality. Aviation collecting can be quite costly. For instance, the nose section of an airplane or an antique propeller can sell for thousands of dollars. If a piece is historically significant, say it comes from an airplane involved in the Second World War, its value could multiply dramatically. The aspect that left me most astonished was the team's flawless coordination. They moved as if they were dismantling a gigantic construction set, with each part assigned its own special place in the bigger picture. It was almost like a dance involving both machinery and people, all working in harmony to accomplish something meaningful. Think about it. A single airplane can yield up to 50,000 parts. Someone has to track each nut, each bolt, and each panel, making sure everything lands in the right container. Logistics teams then see to it that no part gets lost and that every component reaches its intended destination, whether it is a repair center or a recycling facility. Disassembling an airplane is definitely not a matter of taking it apart and forgetting about it. Proper disposal protocols must be followed for all hazardous substances, such as unused fuel, hydraulic fluids, and batteries. Environmental teams and safety inspectors ensure that every step complies with regulations and safeguards the planet. Having witnessed all this, I am convinced that aviation is so much more than just flying. It is about ecology, business, and even a touch of art. Now, whenever I look up and see an airplane cutting across the sky, I find myself wondering what the future holds for it. How about you? So the next time you watch an airplane soar overhead, remember that even after its final flight, it can transform into something far greater. Imagine a motor that can spin up to 23,000 revolutions per minute and produce a level of power that in the past only Formula 1 race cars could achieve. Now picture that motor installed in your Tesla. How did Tesla manage to create such revolutionary electric motors that have made its cars the fastest in the world? From asynchronous motors to the innovative plaid carbon-wrapped versions, today we will dive into the world of technology that is reshaping the automotive industry forever. Are you ready to discover what is inside the most powerful electric motors of our time? Then let us get going. Asynchronous or induction motors were installed on Tesla Model S and Tesla Model X in their earlier versions. Synchronous motors with permanent magnets are used in Tesla Model 3, Tesla Model Y, and later versions of Model S and Model X. Wound rotor motors represent an enhanced technology that combines the benefits of the previous types. Each of these motors has its own unique aspects in manufacturing. Before initiating production, Tesla engineers design the motor using modern modeling software. The design process considers the materials for magnets and windings, the shape of the rotor and stator for maximum efficiency, the cooling system to prevent overheating, the balance of weight, and the positioning of the motor in the car. After completing digital modeling, prototypes are produced and tested under laboratory conditions. Now let us move on to the stage that focuses on the key components. The first component is the stator. It is the heart of the electric motor and the stationary part of the motor, containing copper wire windings. The stator core is made of many thin layers of electrical steel, which helps reduce energy losses from eddy currents. These steel sheets are cut by laser cutting or stamping. The sheets are assembled together and pressed into the form of the stator. The next step is the coil winding process. Automated winding is utilized, along with a precise calculation of the number of turns. In order to boost efficiency, hollow copper wires with coolant flowing inside are used. After the winding, vacuum impregnation with varnish takes place to protect the windings from overheating and damage. We then proceed to the stator assembly stage. The windings are connected to electrical contacts. Temperature sensors are installed to monitor heating. The completed stator is subjected to quality control and testing. The rotor is the moving part of the motor. Tesla uses two types of rotors. An asynchronous rotor with a squirrel cage is employed in induction motors. It is made of aluminum or copper by casting the metal into a mold. A rotor with permanent magnets is used in Tesla's synchronous motors. It contains magnets based on rare earth metals, creating a strong magnetic field. As with the stator, a multi-layer steel structure is used for manufacturing the rotor. The steel sheets are cut and either glued or pressed together into the shape of the rotor. Neodymium magnets are inserted into the rotor body. The magnets are secured by adhesive or mechanical fasteners so that they can withstand rotational speeds of up to 20,000 revolutions per minute. Because the rotor spins at high velocity, perfect balancing is essential to avoid vibrations. The rotor is tested on specialized equipment that automatically adds or removes material to adjust the balance. The next stage is motor cooling. Tesla employs liquid cooling for its electric motors. Coolant circulates through channels in the motor housing, carrying away excess heat. This enables the motor to function at high power levels. The rotor is mounted on bearings for minimal friction. The stator and rotor are placed inside the motor housing. All components are connected according to the design. A controller operates the motor by regulating power and rotational speed. Metal oxide semiconductor. Field effect transistors, or insulated gate bipolar transistors, are employed to convert electric current. We now move on to the final step, which involves filling the system with cold fluid. The coolant is introduced into the cooling system and checked carefully for leaks. Following assembly, every motor undergoes an extensive battery of tests. A no-load test verifies smooth rotation. A load test evaluates efficiency and energy consumption. A thermal test stresses the motor under maximum loads. A noise test measures noise and vibration. Only after passing all these tests successfully does the motor proceed to the production of Tesla vehicles. Manufacturing Tesla's electric motors is a high-technology process that integrates advanced engineering approaches, automated manufacturing, and sophisticated testing methods. Tesla continually improves its motors, making them more efficient, more compact, and more powerful. This technology lets Tesla produce electric vehicles that outdo the competition in power, range, and reliability. The story of how Tesla developed electric motors for its cars is one of innovative technology, risk-taking, and the relentless efforts of engineers. It all started with an ambitious plan to revolutionize the automotive industry, and although initially the company did not produce its own motors, it ultimately became a leader in this domain. Tesla Motors was founded in the year 2003 by a group of engineers, which included Martin Eberhard, Mark Tarpenning, Ian Wright, Jeffrey Brian Straubel, and the future chief of the company, Elon Musk. The main vision was to create an entirely electric car capable of competing with conventional gasoline-powered vehicles. At that time, electric vehicles did exist, but they were slow and inefficient. That was when the Tesla team decided to utilize an asynchronous electric motor, originally patented by Nikola Tesla in the year 1888. Tesla's first electric motor was developed using technology from a company named AC Propulsion, which was creating high-powered electric motors for electric car prototypes. Tesla established a licensing deal with AC Propulsion and adapted its technology for its first model, the Tesla Roadster of the year 2008. This was a three-phase asynchronous motor featuring a rotating magnetic field. It was manufactured with an aluminum rotor, which provided excellent efficiency. The maximum output was 248 horsepower, enabling the Roadster to accelerate to 61 miles per hour in 3 9/10 seconds. Despite the success of this first vehicle, Tesla encountered difficulties with component supplies. The motors were made at external factories, and quality control was lacking. This pushed the company to consider setting up its own production lines. Transitioning to in-house production took place from the year 2010 to the year 2012. When Tesla started developing the Tesla Model S, it became clear that the company needed to manufacture its own electric motors. There were multiple reasons for this. The first reason was cost, since sourcing motors from external suppliers was expensive. Tesla also wanted a highly efficient motor designed to meet its specific requirements, meaning the design had to be optimized. Quality control was the third reason, because in-house production allowed the company to oversee every aspect of manufacturing. In the year 2010, Tesla purchased a plant in Fremont, California, previously owned by General Motors and Toyota. This was a pivotal milestone in scaling up production. In the year 2012, the Tesla Model S became the company's first vehicle to use Tesla's in-house electric motor. It was more powerful and more efficient than the previous generation's motors. The Tesla Model S motor of the year 2012 represented a breakthrough in technology. It was created using asynchronous induction motor principles, with a copper rotor instead of the aluminum rotor that was in the Roadster. The copper rotor raised efficiency and diminished heat losses. The performance version delivered 416 horsepower, enabling acceleration to 61 miles per hour in 4 4/10 seconds. This model drew global attention, and Tesla expanded rapidly thereafter. Let us examine the newer generations of motors from the year 2017 to the year 2020. Although asynchronous motors remained efficient, Tesla's engineers began exploring new motor designs. In the year 2017, during the development of Tesla Model 3, the company chose to adopt synchronous motors with permanent magnets. The Tesla Model 3 motor, starting in the year 2017, is a synchronous motor with permanent magnets. This made the motor smaller, lighter, and more efficient. Neodymium magnets helped reduce energy consumption. The refined cooling system enhanced reliability. This motor became standard in Tesla Model 3 and Tesla Model Y. However, Tesla did not stop using asynchronous motors and continued installing them on the front axle of Tesla Model S and Tesla Model X for dual motor versions. Tesla pushed forward and introduced its plaid carbon-wrapped motor technology, which premiered in the year 2021 in Tesla Model S Plaid. Plaid carbon-wrapped motor is a revolutionary solution. It utilizes a carbon wrapping on the rotor, enabling incredibly high speeds of up to 23,000 revolutions per minute. An improved cooling system endures extreme stresses. The Tesla Model S Plaid can accelerate to 61 miles per hour in only 1 99/100th seconds, making it the fastest production electric car in the world. This technology was entirely developed by Tesla's engineering team and is unmatched by any competitors. Manufacturing electric motors for Tesla cars is a sophisticated and advanced process encompassing pioneering research, modern simulation, automated assembly, and meticulous testing. Tesla gradually evolved from employing asynchronous motors in its early models to integrating state-of-the-art synchronous motors with permanent magnets and the revolutionary plaid carbon-wrapped motor. Through continuous enhancements of its technology, Tesla has produced motors that combine outstanding efficiency, power, and compactness. This enables its electric vehicles to surpass competing models in acceleration, energy consumption, and reliability. Tesla's decision to make electric motors in-house allowed the company to manage quality, reduce costs, and refine designs, proving to be instrumental in its expansion. The unwavering drive toward innovation and the pursuit of new advancements solidify Tesla's role as a leader in electric transportation, shaping the future of the automotive industry. Imagine this. By 2030, the entire world could be threatened by over 12 million short tons of spent lithium-ion batteries. But what actually happens to electric vehicles once they reach the end of their service life? It is not just simple disassembly. It is a high-technology process where even the remaining battery charge is used to power industrial facilities. Meanwhile, steel, aluminum, and plastic go right back into manufacturing, giving a new life to old automobiles. Watch until the end. You will be surprised by how efficient this recycling has become. The cost of electricity for charging is significantly lower than the cost of gasoline or diesel fuel, and the motor runs rather quietly. This, of course, increases the comfort of the ride. The most popular models are produced by Tesla, but there are many other manufacturers on the market, including Nissan, BMW, Audi, Mercedes-Benz, Volkswagen, Porsche, Rivian, Ford, General Motors, and Hyundai, which is quite a lot. However, even an electric vehicle eventually reaches the end of its service life. When the vehicle arrives at this end, it is sent for recycling. First, the car is deregistered, and then it is taken to special facilities that handle disassembly and recycling of vehicles. These can be recycling centers, auto dismantling sites, or recycling factories. Vehicles may be delivered by the owners themselves or by dedicated services that pick up damaged or non-operational cars. Some facilities work with insurance companies or government organizations that coordinate disposal programs. When the car arrives at the site, it is initially inspected to determine which parts can be reused and which must undergo complete disposal. The site is typically an area equipped with bays or specialized zones where all processes take place. Mechanics and equipment operators work here, removing vehicle components both manually and with the help of machines. First, all technical fluids are drained. The car is placed on a special lift or in a separate drainage area. Operators use pumps or remove drain plugs to extract motor oil, transmission fluid, antifreeze, brake fluid, and fuel. The fuel is pumped out with vacuum systems to prevent fire hazards, and the motor oil is collected in containers for later recycling. After that, the disassembly of the vehicle begins. The battery is removed first and sent to a separate recycling process. There, it is tested to determine the level of remaining charge and suitability for reuse. The removal must be done carefully, as the battery contains toxic and flammable materials. This can take from 30 minutes to 60 minutes by itself. If the battery can still hold a charge, it is used in stationary energy systems, for example, to store energy from solar panels. If the battery is completely worn out, it is sent for disposal. To monitor battery condition even before disposal, Tesla, for instance, uses its own software that can remotely evaluate the remaining capacity, the level of cell degradation, and the overall condition of the vehicle's energy system. This makes it possible to determine whether the battery can be used in secondary energy applications or must be fully disassembled. Through this approach, the company reduces the number of batteries immediately sent for disposal, extending their life cycle as stationary energy storage systems for as long as possible. The recycling of Tesla electric vehicles happens in much the same way as the recycling of other electric vehicles. But there are certain specifics due to the battery design, the body materials, and the software. Tesla batteries have a complex modular structure and a high energy density, requiring additional safety measures, including a complete discharge and controlled disassembly. A full discharge of a Tesla battery is carried out at specialized recycling centers, where strict safety measures are followed to avoid the risk of fire or explosion. This is done using special equipment that gradually removes any leftover electrical energy, placing the battery into a safe state. Because lithium-ion batteries maintain a high energy density, they can still hold a substantial charge even after extended use, making the discharge process critically important prior to further recycling. According to estimates, by the end of 2030, around 12 million short tons of spent lithium-ion batteries could end up in landfills if effective recycling systems are not put in place. To discharge the battery, industrial systems of controlled power consumption are connected, gradually drawing off the remaining energy. These machines operate on the principle of creating a controlled electrical load, simulating energy consumption, where electrical energy is converted into heat that is then dissipated by active cooling systems. Another method involves connecting the battery to industrial energy storage systems, which can use the residual charge to power facilities or feed electricity back into the grid. The process occurs in a controlled environment with low humidity to minimize the risk of corrosion and unwanted chemical reactions. The temperature is maintained between 50 degrees Fahrenheit and 68 degrees Fahrenheit because higher temperatures can accelerate degradation of battery cells, while lower temperatures increase the risk of electrolyte instability. The operator oversees discharge parameters through computerized monitoring systems, which record voltage, current, and battery temperature in real time. Once the charge falls to a safe level, typically below 1% of the original capacity, the battery is considered discharged and ready for further disassembly. The battery is taken apart, separating the casing, modules, and electronics. Each module consists of thousands of lithium-ion cells that must be properly recycled to recover valuable metals. The modules are mechanically shredded in specialized installations that operate in an inert gas environment or under liquid nitrogen to prevent spontaneous combustion of any leftover active materials. The resulting shredded mass undergoes either thermal treatment or chemical solutions to remove organic components such as electrolyte and binding substances. After processing, the recovered metals are reused in the production of new batteries, and the remaining materials are disposed of in accordance with environmental standards. Toxic waste is neutralized at specialized facilities. Currently, only about 5% of lithium-ion batteries are recycled worldwide, indicating a major opportunity to improve recycling infrastructure. One key method for recovering valuable materials is hydrometallurgy. This process involves dissolving shredded elements in specialized chemical solutions that allow for the separate extraction of nickel, cobalt, lithium, and other metals. Compared to the traditional pyrometallurgical method, which uses melting at high temperatures, hydrometallurgy is more energy efficient and environmentally safe because it allows the extraction of pure metals without significant air emissions. Thus, the batteries are disassembled, casings and electronic components are recovered, and then the active electrode material is shredded. The resulting shredded mass is referred to as black powder, as it contains oxides and other metal compounds. Next, this powder is dissolved in an acidic environment, using, for instance, sulfuric or hydrochloric acid. This stage is known as acid leaching, during which the metals convert into a solution. As a result, a liquid mixture forms that contains ions of lithium, nickel, cobalt, and other elements. The next step is extraction and selective precipitation. Using reagents such as organic extractants or precipitating agents, specific metals are extracted from the solution. For example, lithium may be precipitated as lithium carbonate or lithium hydroxide, both of which are used in the production of new batteries. Nickel and cobalt can be extracted by altering the alkaline solution or by precipitation using sulfides and hydroxides. After precipitation, the metals undergo additional purification, including filtration and recrystallization. The end products, metal salts or metal oxides, are sent back into production for new battery cathode materials. The efficiency of hydrometallurgy makes it possible to recover over 90% of nickel, cobalt, and manganese, as well as up to 90% of lithium. This significantly reduces the need to mine new resources and promotes a closed-loop battery manufacturing cycle. After disassembling and processing the batteries, the electric vehicle recycling process continues. The motor and transmission are removed if they are suitable for reuse or repair. This can be done by people manually, using wrenches, jacks, and other tools, or by robotic systems that simplify the process. Wheels, radiators, electronics, and glass are also removed, and these components can be sold separately or recycled. Window glass, for instance, is recycled by shredding it into granules, which are then used in construction or to produce new automotive glass. Plastic components, such as bumpers, interior panels, and fuel tanks, are processed by shredding and later used to create new products. Only when all valuable and hazardous components have been removed from the car do they proceed to recycle the body. It may be cut into large pieces using hydraulic shears or sent directly to a shredder. Shredders reduce the metal frame to small fragments, which are then sorted by material type. Steel and aluminum are separated using magnets or electronic sensors, after which they are sent for remelting. Those parts of the vehicle that cannot be recycled may be disposed of by incineration to produce heat energy or buried at specialized landfills. The entire process can take anywhere from a few hours to several days, depending on the type of vehicle and the level of automation at the facility. However, with modern technology, the percentage of materials that can be reused is constantly rising, and it currently exceeds 3/4 of a vehicle's total mass. Imagine a machine that can withstand the blast of a high-explosive device, endure fire from automatic weapons, and keep rolling even with shot-through tires. This is the legendary Hummer, designed for the most dangerous missions. From operations in the Persian Gulf to modern combat zones, over 280,000 armored Hummer vehicles have become an essential part of the United States Army. How do these machines go through their testing? Which materials protect the crew? And why do they produce 70 of them per day? Let us find out. To understand why the Hummer became synonymous with invincibility, one should first look back at its history. In the 1980s, the American automobile company called AM General unveiled a modified Hummer that was initially developed for the civilian market. However, the troops quickly recognized its advantages for modern warfare, especially on the front lines, where soldier protection is paramount and armored vehicles became critically important for safety. A true breakthrough came after the Hummer became the main transport vehicle for the United States military during operations in the Persian Gulf at the beginning of the 1990s. Since the year 1893, over 280,000 Hummer units have been manufactured. But how can one ensure that this off-roader not only endures harsh conditions, but also provides protection in the most hazardous situations? What exactly sets the military armored Hummer apart from civilian models? Let us see how the armored components are constructed to turn these vehicles into a genuine steel shield on wheels. Military Hummer vehicles use specialized armor materials, including composite armor that combines steel plates with ceramic inserts. These materials can withstand shots from a variety of weapons, including automatic rifles and sniper rifles. Moreover, by incorporating composites, these vehicles are not only armored, but also relatively light for their size. The production rate is around 70 vehicles per day. A key structural element of the armored Hummer is the concept of plus armor. This means that multiple layers of protection are added onto the vehicle, enabling maximum defense in a wide range of combat scenarios. There are also additional design modifications, such as reinforced suspension and strengthened tires, allowing the vehicle to keep moving even if one of the tires has been damaged. Another important aspect is the strengthened floor and roof. In military Hummer vehicles, the floor is structurally protected against blasts. Special materials are used to absorb the shockwave, which reduces risk to the crew if the vehicle encounters a minefield or an explosive device. However, armor is only one part of the overall safety level. Each high-mobility multi-purpose wheeled vehicle, commonly known as the Hummer, consists of over 5,000 parts. Combat Hummer vehicles must not only be protected, they must also be real beasts capable of moving through absolutely any conditions. How is this kind of mobility achieved? In order to preserve high off-road capability and endurance, military Hummer models are equipped with a powerful diesel engine. This engine can generate substantial power that lets the vehicle easily travel through desert sands or mountainous routes, even if there is no road at all. A specialized transmission and adapted rear wheels ensure constant stability in the most extreme conditions. Many modern military Hummer vehicles integrate intelligent control systems that allow the engine and transmission to adapt to the terrain. This significantly boosts maneuverability and endurance during large-scale strategic movements. Armored versions receive steel that is half an inch thick, along with bullet-resistant glass that is 1.5 inches thick. Besides armor, electronic safety systems are vital, such as sensors that detect mines and explosive devices, along with systems designed to remain fire-resistant. They add another layer of protection for the crew, which is particularly critical in combat situations. What else is worth mentioning when talking about armored Hummer vehicles? There are several technical considerations to bear in mind. Military Hummer versions often feature specialized camouflage coatings that help them blend into the environment. This is crucial for enhancing survivability on the battlefield, where every detail can make a difference. Interestingly, the Hummer is not a static vehicle. Its design allows modifications based on mission needs. These can include additional weapon systems, medical equipment, or other specialized modules, depending on the task at hand. A military Hummer can carry up to 2,500 pounds of cargo or tow up to 7,500 pounds. Producing armored Hummer vehicles is a complex and lengthy process that demands highly skilled engineers and advanced technology. Everything starts with meticulous planning. Engineers account for every aspect, from improved mechanical components to resilience during blasts. Multiple prototypes are built, each undergoing a battery of tests. They are dropped from heights, fired upon, and examined for endurance in different conditions. Previously, AM General, the company that originally created the legendary Humvee, was in charge of production. However, in the year 2020, the license to manufacture new military vehicles was granted to Oshkosh Defense. As a result, combat Hummer vehicles are gradually being replaced by the Joint Light Tactical Vehicle, a more modern armored off-road vehicle. Therefore, military and civilian versions are produced separately, using different factories, technologies, and even materials. The body and armored panels are cut using laser or plasma machines, and then they are welded by robots and highly qualified specialists. Precision is crucial, because all seams must be airtight to enhance blast resistance. The Hummer is built on a robust steel frame, designed to withstand high loads. The chassis and engine are assembled separately, then tested for functionality. Only after that are they joined with the body. Once the main parts are put together, the vehicle is fitted with armored panels and additional protection. This stage is time-consuming because every component must be installed with the utmost precision. The interior of a military Hummer is nothing like that of a civilian vehicle. Everything is dedicated to functionality. Some models have air conditioning, which is essential in desert conditions. After assembly, the vehicle is painted with special scratch and corrosion-resistant paints. Several options are employed: desert camouflage for sandy regions, woodland or urban camouflage for the respective environments, and anti-radar coating to reduce visibility on radar systems. This is no ordinary paint. It is formulated to withstand heat, freezing temperatures, and the impact of blasts. The high-mobility multi-purpose wheeled vehicle is not produced in the same way as mass-market civilian cars. It is manufactured in relatively small batches, so fully automated production is impractical. At the same time, certain processes, such as welding and painting, are streamlined by a conveyor system for speed and consistency. Each high-mobility multi-purpose wheeled vehicle is equipped with a 396 cubic inch diesel engine that outputs 190 horsepower. This powerful diesel engine is engineered to operate under extreme conditions. The transmission is a 4-speed automatic adapted for off-road use. The vehicle has permanent 4-wheel drive and automatic differential locks. It accelerates to 37 miles per hour in approximately 17 seconds. It is slow, but speed is not the main goal for the military. For military transport, the priorities are off-road performance, reliability, and endurance. The high-mobility multi-purpose wheeled vehicle is not designed for swift maneuvers, but for traveling over any type of terrain. It has a high ground clearance of 16 inches, which allows it to clear rocks, ditches, and logs. Full-time 4-wheel drive and differential locks prevent it from getting stuck in mud or sand. The engine and fuel system are protected to withstand fire and blasts. There is minimal onboard electronics, meaning fewer things can break down in the field. It can continue moving on punctured tires. Special inserts allow driving even after the tire has been hit by a bullet. Its payload capacity allows transporting ammunition, injured personnel, and weapons ranging from machine guns to anti-missile systems. It may not be the fastest ride, but it will get you where others simply cannot go. The standard military high-mobility multi-purpose wheeled vehicle initially did not have armor, but since the year 2000, most models have received protection against small arms fire and shrapnel. Configurations vary, from soft body transport versions to the most widespread ones, capable of withstanding a high explosive device blast of up to 13 pounds. There are models with protection systems against chemical, biological, and nuclear weapons. Assembling a single high-mobility multi-purpose wheeled vehicle takes from 3 to 5 days, depending on the armor. At the AM General facility, where they build the high-mobility multi-purpose wheeled vehicle, there can be up to 3,000 workers in one workshop. However, only about 25 or 30 individuals work on assembling a specific vehicle at any given time. These include welders, mechanics, electricians, and armor specialists, each carrying out their tasks at each stage of the production line. The more complex the version, the more time and personnel are required. Before they are shipped, all high-mobility multi-purpose wheeled vehicles undergo 310 miles of test trials across off-road terrain, water, and dust. You already know how the Hummer is painted, but allow me to elaborate on the special matte paint known as chemical agent-resistant coating, which has several important properties. It does not reflect infrared light, making it harder to detect the vehicle with thermal imaging and night vision equipment. It resists chemical attacks. Its formulation makes it easier to wash off hazardous substances following chemical contamination. It withstands scratches and corrosion, enduring impacts from branches, sand, rain, sun, and aggressive liquids. The matte finish eliminates glare, which is critical for battlefield camouflage. The painting process involves multiple layers that are applied to the aluminum body and armored panels. Every year, more than 12 million cars are scrapped worldwide, and this has become a massive industry running like clockwork. Imagine this. Your old ride could turn into a brand new skyscraper, and that worn-out engine might end up in a military battleship. But what actually happens to cars that have reached the end of the road? They are not simply tossed away. 90% of their materials get recycled. How are cars dismantled, crushed, and literally torn apart to be turned into something new? Today, we are taking a deep dive into this process. Why can you not just leave your old car sitting in the backyard? Well, first of all, it is illegal. Unless you live somewhere where keeping a car on bricks in your yard is completely fine. Second, old cars leak fluids, motor oil, antifreeze, transmission fluid, that can seriously damage the environment. Third, they take up space that could be used for something better, like a new car or even a barbecue grill. So, what are your options? If your car is still somewhat functional, you can sell it for parts. Even if the engine is done for, many components still have value. The battery, if it is still working, can be sold separately or taken to a recycling center. Tires, if the tread is still decent, can be resold. The catalytic converter contains precious metals like platinum, palladium, and rhodium, making it highly valuable. Headlights, mirrors, doors, there is always someone looking for replacement parts. You can sell them on Facebook Marketplace, Craigslist, or local auto shops that buy used parts. If your car is so far gone that even a tow truck refuses to take it, scrapping it for metal is the way to go. On average, scrap metal prices range from $100 to $300 per 2,000 pounds, meaning a regular sedan could get you anywhere from $200 to $600. Before dropping it off, make sure you have the proper paperwork, remove all personal belongings from the interior, and if possible, drain the fluids. Many scrapyards will pick up the car themselves, especially if it is undrivable. How about donating it to charity? In the United States, plenty of organizations accept cars as donations, even if they are not running. Some examples include Cars for Kids, Goodwill car donations, and Wheels for Wishes. You just make a call, they tow it away, and you get a tax deduction. Plus, it feels good knowing your old clunker is helping someone in need. From time to time, government programs allow you to trade in an old vehicle for compensation. In California, for instance, the Consumer Assistance Program offers up to $1,500 for cars that fail to meet environmental standards. It is worth checking if similar programs exist in your state because this might be the most profitable option. Do not leave your car abandoned on the street. That could result in fines or impoundment. Do not try to dismantle it yourself unless you know what you are doing. Some parts, like the fuel tank or battery, can be hazardous. And do not confuse proper recycling with illegal sales. Many states have strict regulations about selling non-operational vehicles without the right documentation. The key is doing it correctly to avoid trouble and protect the environment. In movies, we often see massive junkyards filled with rusting cars under the scorching sun. In reality, most vehicles do not just sit there. Modern recycling is a well-organized process where nearly 90% of materials get repurposed. If a car is beyond repair, it moves on to the dismantling stage. You already know about the initial teardown. After that, the car goes into a hydraulic press, the same machine you have probably seen in movies. It compresses the car into a compact cube, reducing its size by several times. These crushed cars are then sent to massive industrial shredders, huge machines that literally rip the car apart. After that, the shredded metal and plastic move on to sorting. Sorting is done using magnetic separators, which separate metals. Steel and iron are the easiest to extract since they are attracted to magnets. Aluminum, copper, and brass are removed using eddy currents and other techniques. Plastics, glass, and rubber are collected separately, although not everything can be recycled. Once sorted, the materials go to specialized recycling plants. Steel and aluminum are melted down and used to manufacture new cars, construction materials, household appliances, and more. Wheel rims and engine blocks are often turned into new auto parts. Components like bumpers, dashboards, and interior panels are shredded and reused for making furniture, insulation, or even new cars. Automotive glass contains a plastic layer inside, making it harder to recycle, but some companies repurpose it into construction materials. Tires do not decompose and are an environmental hazard, so they are repurposed as much as possible. They are turned into asphalt granules, rubber flooring for playgrounds, and even fuel for cement plants. 99% of car batteries are recycled. The lead is melted down, and the acid is either neutralized or reused. Despite all these processes, about 10 to 20% of car waste remains non-recyclable. This includes certain plastics, adhesive materials in upholstery, and textile or leather interior elements. Researchers are working on new disposal methods, such as pyrolysis, breaking materials down at high temperatures without oxygen, or using biodegradable materials for future vehicles. Today, around 12 million cars are recycled in the United States every year, making it one of the most advanced recycling industries. But back when cars first started taking over the roads, nobody really thought about what to do with them once they stopped working. Picture the early 20th century. Ford releases the legendary Model T. Cars become affordable to the masses, but what happens when they break down? In the early 1900s, old cars were often just left on the roadside or dumped in forests. Many were abandoned in backyards, slowly swallowed by weeds. Some cities even tossed them into rivers or burned them, simply because there was no system in place. Over time, scrapyards emerged, where enterprising individuals collected metal from wrecked cars, melted it down, and repurposed it. By the 1920s and 30s, metal was in high demand for construction, turning old cars into valuable resources. During World War II, the United States and Europe faced an enormous need for steel and other metals. Suddenly, junk cars became a gold mine. Governments even encouraged citizens to turn in their abandoned vehicles for scrap to produce tanks, weapons, and military equipment. By the end of the war, car recycling had become a structured industry, and businesses started opening specialized vehicle recycling plants. In the 1950s and 60s, cars became more affordable. People bought them in droves and just as quickly discarded old models. Huge car graveyards emerged, where vehicles simply rusted away, taking up massive amounts of space. Soon, environmentalists raised concerns: oil leaks, gasoline spills, lead contamination — gasoline still contained lead back then — and other toxins were polluting the land and water. This pushed governments worldwide to implement stricter recycling regulations. By the 1970s, the first serious car recycling programs were introduced. Since the 1980s, vehicle recycling has become more systematized. Companies started using automated shredders to rapidly dismantle cars. Today, modern cars are about 80% recyclable, but manufacturers are working to push that number up by another 10%. In Japan and Europe, laws require automakers to take back their old models for recycling, encouraging the production of more eco-friendly vehicles. Recycling metal from old cars saves up to 74% of the energy compared to producing new metal. Some countries have extremely strict environmental standards: Germany, Switzerland, and Japan. In these places, before cars are crushed, they are burned in specialized facilities to remove plastic residues and other combustible materials. Sounds interesting? Absolutely. This process, called pyrolysis, happens in industrial furnaces designed for thermal decomposition. Once the vehicle fluids are drained and key components are removed, the car is placed in a high-temperature chamber. The temperature inside ranges from 800 to 1,200 degrees Fahrenheit. Materials break down without oxygen, causing plastics, adhesives, textiles, and other organic materials to evaporate, leaving behind only the metal frame. The gaseous byproducts go through advanced filtration systems to capture heavy metals and toxic compounds. The result: minimal emissions and a cleaned-out metal shell, ready for crushing or smelting. Every single day, airplanes across the world consume more than 5 million barrels of aviation fuel. This fuel is the lifeblood of aviation. Without it, not a single jetliner would take off. But have you ever wondered how it is made? From oil refineries to the ultra-pure tanks inside aircraft, the journey of jet fuel is packed with chemical secrets, strict regulations, and even technologies originally developed for military fighter jets. Today, we are pulling back the curtain on this fascinating process and uncovering all its secrets. Jet fuel is a crucial component of the aviation industry. It must meet stringent quality standards to ensure the stable operation of both turbojet and turboprop engines. The primary source for jet fuel production is crude oil, which undergoes a complex technological journey from extraction to the final product. It was obtained through the distillation of crude oil. In the year 1903, the Wright brothers made the first controlled flight with the Wright Flyer, powered by a gasoline engine. In the early days of aviation, gasoline remained the primary fuel, as piston aircraft engines required a high degree of fuel volatility. However, during the 1920s and 1930s, engineers began considering kerosene as an alternative to gasoline due to its higher energy density, making it more suitable for high-altitude flights. German engineer Hans von Ohain and British designer Frank Whittle independently developed the first operational jet engines. Can you believe it? It is true what they say. Ideas are in the air. So, in the year 1939, Germany tested the first jet aircraft, the Heinkel He 178, which ran on specially refined kerosene. In the year 1941, Britain responded to the Nazis by launching the Gloucester E into production, the first British jet aircraft. Around the same time, engineers began developing special types of kerosene that met the demands of jet engines. Military nations involved in the war experimented with various fuel formulations to ensure high energy density, resistance to low temperatures, and low corrosiveness for fuel systems. During the war, jet fuel had a primitive composition, but over time, its standards improved significantly. After the devastating Second World War, jet aviation began rapidly advancing. This created a demand for improved fuel that could provide reliability at high altitudes, better thermal stability, and the absence of harmful impurities. In the 1950s, the first standardized types of jet fuel emerged. Let's take a look at them. JP1, developed in the year 1944, was an early standard for military aviation. JP4, introduced in the year 1950, was a blend of kerosene and gasoline that improved performance in cold temperatures. JP5, introduced in the year 1952, had a higher flash point and was used on US aircraft carriers. Commercial aviation also introduced its own standards, and in the 1950s, Jet A and Jet A1 were introduced as the primary fuels for commercial aircraft. With the development of supersonic aviation, such as the Concorde, and new generation military aircraft, the demand for higher quality fuel increased. Fuel now needed a lower freezing point, as flights took place at extremely high altitudes. This led to the introduction of anti-static and anti-corrosion additives, improving safety. Fuel systems were also designed to prevent icing, as jet fuel could cool down to -40 degrees Fahrenheit or lower. In the 1980s, the military adopted JP8, replacing JP4. This new standard contained fewer volatile components, making it safer to store and transport. The 1990s marked the beginning of the modern era of jet fuel production. So, let's move on to the steps involved in making jet fuel today, starting with crude oil extraction. Jet fuel is derived from hydrocarbons found in crude oil or natural gas. There are several methods for extracting crude oil. The first method is natural pressure extraction, where oil flows to the surface due to its own pressure. This is common in young oil fields. The second method is mechanical pumping, where pumps are used to lift the liquid to the surface. The third method is secondary recovery, where water or gas is injected into the reservoir to increase pressure and stimulate oil flow. Once extracted, crude oil contains impurities such as water, gases, and solid particles that must be removed before refining. Before transportation to the refinery, crude oil undergoes purification. First, water is separated using separators and chemical agents to remove emulsions. Next, degassing removes light gaseous hydrocarbons. Finally, filtration removes solid particles. In storage tanks, the flow slows down, allowing heavier particles to settle, while lighter fractions rise to the top. After this preparation, crude oil is transported to refineries through pipelines or by tanker ships. The next step is the separation of crude oil into different fractions. Let me explain how this process works. The process begins by heating crude oil to temperatures between 662 and 752 degrees Fahrenheit inside a massive distillation column. Through evaporation and condensation, we obtain different fractions: gaseous hydrocarbons, gasoline, kerosene, diesel fuel, and residual fuel oil. The gaseous hydrocarbons include methane, ethane, propane, and butane. The kerosene fraction serves as the primary raw material for jet fuel and undergoes further purification. To improve the quality of the kerosene fraction, it is treated to remove sulfur, nitrogen, and oxygen-containing compounds through hydroprocessing. This process occurs under pressures ranging from 30 to 80 atmospheres and at temperatures between 572 and 752 degrees Fahrenheit, using catalysts such as nickel molybdenum or cobalt molybdenum compounds. As a result, sulfur content is reduced, minimizing corrosion and harmful emissions. Additionally, fuel stability improves, allowing for longer storage without sediment formation. If crude oil does not contain enough kerosene fraction, catalytic cracking or hydrocracking is used to break heavier fractions into lighter ones. Catalytic cracking employs catalysts to break large molecules into smaller ones, while hydrocracking uses hydrogen to produce stable hydrocarbons. These processes help increase the yield of kerosene for jet fuel. After purification and modification, special additives are added to the kerosene fraction to enhance its properties. Antioxidants prevent sediment formation and maintain fuel system cleanliness. Anti-static additives reduce the risk of electrostatic charge buildup during refueling. Anti-corrosion agents protect fuel tanks from corrosion. Anti-freezing additives ensure stability at low temperatures. After additives are introduced, the fuel undergoes final filtration and preparation for distribution. To meet international standards, jet fuel undergoes strict quality testing. Viscosity determines fluidity at low temperatures. The freezing point for Jet A1 must not exceed -52.6 degrees Fahrenheit. The heat of combustion must be at least 18,400 British thermal units per pound. Water content must not exceed 0.46 0.02 of a grain. Electrical conductivity ensures safe refueling without sparks. If the fuel fails to meet standards, it is sent for reprocessing. And now, we reach the final stage of our journey. The finished jet fuel is stored in tanks with moisture and temperature protection. It is transported primarily through pipelines to airports. Large volumes are shipped by rail tankers. Tanker ships handle international deliveries. Trucks deliver fuel to remote airports. During transportation, it is crucial to prevent contamination with water or foreign substances that could compromise fuel quality. By the year 2025, the United States is projected to consume nearly 2 million barrels of aviation fuel per day, totaling approximately 86 million tons per year. As one of the world's largest consumers of jet fuel, the global demand is expected to be significantly higher. The aviation industry is actively working on developing renewable jet fuels to reduce greenhouse gas emissions and improve sustainability. With advancements in technology and environmental regulations, the future will see wider use of biofuels and synthetic alternatives, making aviation more eco-friendly. And most importantly, jet fuel keeps airplanes flying. The next time you board a plane for a vacation or business trip, remember the complex production process that brought that fuel to the aircraft. I think it is worth it. What do you think? Every year, more than 500 billion matches are produced worldwide. That means around 16,000 matches ignite every second. But have you ever wondered how these tiny wooden sticks go through a complex manufacturing process before they end up in your hands? Today, we are diving into the fascinating world of match production, from selecting the right wood to applying the chemical coating that allows them to ignite with a single strike. You will learn how modern factories produce millions of matches daily, what materials they use, and why matches continue to thrive in the market even in the 21st century. The matches we are familiar with first appeared in the 19th century. Let's take a detailed look at each stage of match production. I will tell you all about it, from raw material selection to packaging the final product. The primary material for matchsticks is wood, carefully chosen for its properties. Softwood species are mostly used. Aspen has a uniform structure, is easy to process, does not crack, and provides consistent burning. Poplar is known for being lightweight and widely available. Pine is used less frequently due to its high resin content, but in some regions, it is carefully treated to remove the resin before use. Many manufacturers aim to use waste from the woodworking industry, reducing costs and making production more eco-friendly. The wood is stripped of its bark, sorted, and cut into transportable logs before being sent to the factory. At the factory, the wood is loaded into special drums for cleaning. The logs are then sliced into thin sheets, resembling ribbons. This is done using precision machines with adjustable blades. The ribbons undergo thickness uniformity checks since the quality of the final match depends on it. After slicing the ribbons, they are cut into individual matchsticks. On average, a standard match measures between 1.65 inches and 1.77 inches in length, with a thickness of approximately 0.79 inches. Tell me, did you just measure that too? I do not want to be the only one doing it. The blanks then go through a drying system, reducing their moisture content to an optimal level, no more than 6 or 8%. For additional protection, the blanks are treated with antiseptic solutions to prevent mold, fungi, and insect damage. After this treatment, the matchsticks move to the assembly conveyor. The chemical mixture for match heads is prepared in separate facilities. It is a complex combination of several key components. Oxidizers release oxygen during combustion. Sulfur or other flammable substances ensure stable burning. Phosphorus is the main element that enables instant ignition upon friction. Dyes give the heads their characteristic colors: red, green, black, and more. Adhesives bind the components together. The ingredients are mixed in specialized equipment, and the finished mixture is poured into storage tanks. For worker safety and to prevent spontaneous combustion, all operations take place in explosion-proof rooms with strict temperature control. By the way, did you know that in the year 1826, English pharmacist John Walker invented friction matches? His friction matches consisted of a stick coated with a mixture of antimony sulfide and potassium chlorate. Then, in the 1830s, Frenchman Charles Sorier improved them by using red phosphorus, which was less toxic and safer than yellow phosphorus. These matches could ignite only when struck against a specially prepared surface on the box, becoming the prototype of modern safety matches. After applying the chemical mixture, the matchsticks are sent to drying chambers. Here, they undergo a drying process that lasts approximately 2 or 3 hours. These chambers maintain a controlled temperature, ensuring the mixture solidifies evenly. This treatment gives the match heads the necessary strength to prevent crumbling or flaking, even during long-term storage or transportation. This stage is crucial since it forms the core functional part of the match, the head, which ensures its usability and durability. Thanks to modern technology and rigorous quality control, the final product is not only convenient, but also entirely safe for users. While the matches are drying, a separate production line manufactures matchboxes. Cardboard is used, going through several steps, which we will now explore together. Step 1. cutting sheets into blanks. Step 2. Printing labels, which may include either simple manufacturer information or colorful designs depending on the order. Step 3. Forming the boxes using specialized machines that fold and glue them together. Next, a special abrasive coating is applied to the inner side of the matchbox. This mixture of phosphorus, glue, and quartz sand ensures match ignition. Afterward, the dried matches move onto a conveyor belt, where they are cut to a perfectly uniform length. Then, precision dosing machines distribute the matchsticks into the boxes. Each box is filled with an exact number of matches, usually 40, 50, or 100, depending on the format. Once filled, the boxes are automatically sealed and sent to the packaging line for shipping and storage. The finished match blocks are labeled and sorted onto pallets before being loaded onto trucks for delivery to stores or wholesale suppliers. Now we are in the final stretch of match production, the concluding stage that wraps up this long, intricate, and carefully planned process. At this stage, the finished matchboxes are carefully grouped into bundles, usually containing 10 or 12 boxes. These bundles are tightly wrapped in transparent polyethylene film, which serves several important functions. First, this packaging protects the matches from moisture, preserving their quality during transportation and long-term storage. Second, it makes the products easier to handle and distribute. After packaging, the bundles are labeled according to logistics requirements. Each package includes information about the manufacturer, production date, batch number, and other necessary details. The products are then arranged on pallets, optimizing transportation efficiency. Loaded pallets are transported to trucks, which deliver the finished matches to stores, wholesale warehouses, or even export them abroad. It is important to note that strict quality control is conducted at every stage of the production process. This ensures that the matches meet high standards and satisfy consumer expectations. The wood's uniformity is checked to ensure it is strong, free of cracks and defects, as it forms the foundation of every match. The durability of the match heads is tested to ensure the chemical composition does not crumble or flake, making the matches reliable for use. The ease of ignition against the abrasive surface is controlled, ensuring matches ignite on the first strike while remaining safe for transportation. Match production is a combination of high-tech equipment, natural raw materials, and strict quality control. Each match goes through dozens of steps before reaching store shelves and, ultimately, your hands. Thanks to automation, eco-friendliness, and safe working conditions, the match industry remains an essential part of many economies. Match production is a complex, multi-stage process that integrates modern high-tech equipment, natural raw materials, and strict control at every stage. The process begins with material preparation, including wood and special chemical mixtures for coating match heads, and ends with packaging the final product. Each individual match undergoes dozens of technological operations, including wood processing, chemical application, drying, and quality inspection before reaching store shelves. Automation and eco-friendly technologies ensure that modern match production meets high safety standards for both workers and the environment. Additionally, manufacturers focus on resource conservation and waste minimization, making the process more sustainable. Matches remain an essential part of everyday life for many people, and their production is an important economic sector that supports traditional industries, creates jobs, and generates stable income for many businesses. By combining advanced technology, sustainability, and a commitment to quality and safety, the match industry continues to thrive in the modern world. It might seem that, in the 21st century, lighters should have completely replaced matches, right? But the reality is not that simple. First, matches are an extremely cheap and compact way to start a fire, requiring no additional costs or recharging. They are also highly convenient for short-term use, such as lighting candles, campfires, or outdoor cooking equipment. Another reason is that matches carry a sense of nostalgia and tradition, often associated with a certain aesthetic or atmosphere. In some cases, they are even used in ceremonies, where this small gesture holds symbolic significance. Safety is another factor. Matches do not have mechanical parts or batteries that can fail. For some users, matches provide greater confidence in reliability. So, the next time you strike a match, remember how many people and machines worked to bring it into your hands. And you know what? They did an amazing job. One factory, 1 million chickens, over 500,000 eggs every single day, and roughly 120 tons of feed. Imagine that. Automated systems handle feeding, sorting, and packaging to keep this process running non-stop. Every day, these chickens drink enough water to fill 29 Olympic-sized swimming pools. Modern tech makes it possible for a chicken metropolis to run with just about 100 workers. How is that even possible? You'll find out in our video. Chickens on large farms are kept either in cages or in free-range systems. If they're in cages, these are arranged in multi-level rows. Think of it like a chicken skyscraper. Each cage has everything a chicken needs: perches, feeders, drinkers, and even a sloped floor so eggs roll straight into a collection tray after being laid. On the other hand, free-range chickens have more space to roam. They get access to the outdoors, though it's usually not a lush green field, but specially designed enclosed areas. Even in these systems, everything is organized down to the smallest detail. This factory houses 1 million chickens in a caged system, covering over 25 acres. By comparison, the same number of birds in a free-range system would need more than 80 acres. Here's another fascinating fact. Modern farms maximize vertical space, especially in caged systems, to optimize efficiency. Most of the area is used for multi-level production facilities, housing cages, feed silos, sorting rooms, and staff areas. The chickens are fed specially formulated feed to ensure consistent egg production. This feed is a mix of grains, corn, soybeans, and added vitamins and minerals. And here's the kicker. Every single gram of feed is crucial because it determines the quality and quantity of the eggs. Feed is constantly tested for protein, calcium, and potential contaminants. Some farms even add herbal extracts to keep the chickens healthy without antibiotics. Large farms use automated feeding systems. Feed is distributed through pipes or conveyor belts, filling feeders in the cages or barns. Sensors monitor feed levels and automatically dispense more when needed. Chickens receive feed tailored to their stage of life. Young chicks get starter feed rich in protein and energy. Layers receive feed high in calcium, vitamins, and trace minerals for strong eggshells. Chickens nearing the end of their life cycle get finisher feed. The feed also includes additives to support digestive health, boost immunity, and improve egg quality. Chickens are fed 2 to 4 times daily, depending on the system. Some farms schedule feedings right before laying time to encourage consistent egg production. Layers consume about 5 ounces of feed daily. For 1 million chickens, that's nearly 120 tons of feed every day, or about 40,000 tons annually. Just look at the massive silos and transportation systems needed to manage that volume. In addition to feed, chickens are provided with clean drinking water. Nipple drinkers allow them to drink without spilling. 1 million chickens require over 2.5 million gallons of water annually, roughly the amount held by 29 Olympic-sized swimming pools. Feed is stored in silos, protected from moisture and mold. Its nutritional content is constantly analyzed to ensure quality. Modern farms even use software to track how much feed each group of chickens consumes. In some free-range systems, chickens are also allowed to forage for grass, insects, and grains, making their diet more natural. But even here, the primary feed is delivered automatically. Feeding systems are key to ensuring chickens lay eggs consistently and stay healthy throughout their production cycle. After laying, eggs roll into trays through special chutes. From there, they're transported on conveyor belts. Imagine an endless line of eggs floating towards sorting machines. These machines check for defects, discarding damaged or undersized eggs using special scanners that literally illuminate the eggs. It's futuristic. Before packaging, eggs are carefully washed in warm water with gentle disinfectants. This step ensures their safety. And no, it's not just a quick rinse. Eggs go through several warm water baths to remove dirt and microorganisms. Then they're dried and coated with a thin layer of food-grade wax for protection. At the sorting stage, each egg is weighed and categorized: large, medium, and so on. Depending on the category, eggs are packed into boxes. Simultaneously, shells are dried to prevent moisture that could lead to bacterial growth. Clean inspected eggs are placed in cartons or plastic trays by automated arms. Packaging includes details like packing date, grade, size, and producer certification. Storing such a daily volume of eggs requires refrigerators with over 70,000 cubic feet of capacity, about 40 large refrigerated trucks. After packaging, eggs are sent to storage facilities or logistics centers. Here, strict temperature controls between 32 and 40 degrees Fahrenheit keep them fresh. Eggs are transported in refrigerated trucks to prevent spoilage. At distribution centers, eggs are sorted based on supermarket orders and quickly delivered to stores or markets. Modern logistics systems reduce the time from farm to shelf to just a few days. Once on supermarket shelves, eggs are stored in refrigerators to maintain freshness. Consistent storage temperatures are crucial because sudden changes can cause condensation, increasing the risk of shell contamination. Consumers choose eggs based on size, price, brand, or labels like organic or free range. At home, eggs are stored in the fridge. Freshness is easy to check. If an egg sinks in water, it's good to use. Although large-scale farms are resource-intensive, many are adopting eco-friendly initiatives. These efforts not only reduce environmental impact, but also meet growing consumer demand for sustainable products. Some farms invest in solar panels on facility roofs or nearby solar fields, covering 30 to 50% of their energy needs. Chicken manure, a natural byproduct of any farm, is a valuable resource for agriculture. Chickens produce as much manure as the feed they consume, over 100 tons daily. Manure is collected, dried, and processed into organic fertilizer. Instead of creating waste, farms provide a product that restores soil fertility and reduces reliance on chemical fertilizers. Fertilizer production from chicken manure also lowers methane emissions compared to natural decomposition. Did you know a single chicken lays 1 egg a day? Of course, 1 million chickens don't equal 1 million eggs daily, since some aren't laying yet or have stopped laying. Still, production numbers are impressive, over 500,000 eggs each day. Stack those eggs, and you'd get a column over 29,500 feet tall, 23 times higher than the orbit of the International Space Station. Younger chickens lay eggs almost daily, while older ones do so less frequently. Balanced feed helps boost egg production. Factors like temperature, lighting, and stress-free conditions also play a big role. During winter, shorter daylight hours can slightly reduce laying rates. American eggs are rich in protein, vitamins D and B12, iron, and other nutrients. There are even eggs with higher omega-3 content, depending on the chicken's diet. You know what surprised me the most? The small workforce. Modern automation allows a 1 million chicken farm to operate with just 100 or so workers. Their tasks include equipment monitoring, veterinary care, and managing feed and egg logistics. A farm of this size can generate up to $50 million in annual revenue. This makes a significant contribution to the local economy, especially in logistics, feed production, and processing. These numbers show just how massive and coordinated the effort is to keep a steady flow of eggs heading to stores and ultimately to our kitchens. Every year, more than 22,000 short tons of amethyst are mined all over the world. But how do these unique purple crystals end up on display in jewelry stores? Picture enormous geodes, each roughly the size of a person, packed with dazzling crystals that miners extract from remote regions in Brazil, Uruguay, and Africa. Some of these geodes are so rare that they are transported by helicopters. However, did you know that only about 10% of all discovered amethysts are of jewelry quality? Let us dive into a world where nature creates masterpieces and humankind unveils them for everyone to see. Brazil is one of the largest suppliers of amethyst on the planet. The main deposits are located in the states of Rio Grande do Sul and Minas Gerais. In Brazil, amethyst geodes are often found, which are hollow stone formations lined with crystals on the inside. Some geodes can reach over 9 feet in height. Uruguay is famous for its amethyst that has a rich, dark purple hue. This stone is usually of higher quality than the Brazilian variety. Geodes from Uruguay are considered extremely valuable because of their depth of color. The African continent, particularly Zambia, is also an important source of amethyst. Zambian amethysts feature a unique purple color with a bluish tint. They are mined in considerable volume, but the deposits are located in hard-to-reach regions, making transportation more complicated. Amethyst deposits in the United States are not as large-scale as in Brazil or Uruguay, but they have their own special history and appeal. The amethyst found in the United States is prized for its vibrant coloring, historical significance, and local popularity. So, let us take a closer look at the main locations and their distinctive features. Four Peaks is the most renowned and likely the largest amethyst deposit in the United States, situated in Arizona, at an elevation of about 7,545 feet above sea level. The amethyst from Four Peaks is noted for its deep purple color, with a subtle reddish glow. Many believe these stones can compete in quality with even the most valuable specimens from Uruguay. The deposit is located in an extremely challenging spot. There are no roads, so miners and equipment are transported by helicopters or on mules. This is one reason why stones from this deposit are so expensive. The mining process is physically demanding and costly. Most of these mines are small, and much of the work is done manually to avoid damaging the crystals. A modest region in the northern part of Georgia is home to lighter, pastel-toned amethysts. Although the deposits are not as extensive as those in Arizona, the stones exhibit a unique clarity and a pleasant purple hue suitable for more affordable jewelry. Local specimens are often mined in small private shafts or even during special tours that allow tourists to try their hand at being treasure hunters. This aspect adds a certain charm to Georgia amethysts, as they become both a souvenir and a cherished memory. The Creed area in Colorado was once more famous for its silver mines. However, there are certain spots where amethyst deposits can be found as well. These stones tend to be lighter in color and less intense in saturation, yet they possess interesting inclusions that give them a unique character. Amethysts from Creed are frequently used to make cabochons, which are smooth, unfacetted stones suited for decorative ornaments. Amethyst usually forms in volcanic rocks, where high temperature and pressure conditions cause quartz to absorb iron impurities, then cool over thousands of years. The outcome is a deep purple crystal that makes you pause and exclaim, "Wow!" For example, in Brazil, miners uncover enormous geodes lined with crystals. Sometimes these geodes are so large that they appear at exhibitions, where people take photos beside them, as if they were standing next to a work of art. Now imagine this scene, a team of miners wearing hard hats, equipped with headlamps and pickaxes, searching for just the right pockets of stone where these priceless cocoons lie hidden. Believe me, it is no simple task. Today, miners do not rely solely on luck in their pursuit of amethyst. Their primary allies these days are science and technology. The process starts with detailed geological mapping. Geologists investigate regions that are well known for containing abundant quartz, the primary mineral from which amethyst arises. For instance, in Brazil, the world's largest amethyst producer, researchers target geological formations ranging in age from 50 million years to 200 million years. One of the most advanced tools is high-resolution satellite imagery. Through spectral analysis of the colors on the Earth's surface, specialists can pinpoint hues that hint at the presence of specific minerals, including quartz. Moreover, seismic sensors contribute to the creation of three-dimensional models of the underground layers of soil. These devices detect even minute reflected waves that tell the story of the materials hidden below the surface. Yet, as strange as it may sound, intuition and hands-on experience still play a huge role. For instance, miners in Rio Grande do Sul in Brazil claim that deep reddish-brown soil nearly always indicates proximity to amethyst. Such observations help them concentrate their efforts exactly where the odds of discovering stones are the greatest. Statistics show that only about 5 to 10% of all areas that look promising based on maps or satellite data actually harbor commercially valuable deposits. In Brazil, which accounts for over 40% of the global amethyst market, dozens of new zones are surveyed every year, but only a handful proceed to the extraction phase. The average depth of an amethyst mining site seldom exceeds a few dozen feet, but these locations demand enormous amounts of preliminary work. According to the United States Bureau of Mines, launching a single mine may require as long as 3 years and cost anywhere from $50,000 to $100,000 before unearthing even a small pocket of amethyst. This illustrates how labor-intensive and expensive the quest can be, even for gems as popular as amethyst. Ultimately, technology, expertise, and a hint of intuition collaborate to uncover those mysterious purple treasures that we admire in jewelry. Although the probability of finding the ideal crystal is slim and the miner's work is strenuous, the reward is unquestionably worthwhile. The amethyst extracted from a mine looks nothing like what you see in a display case. It is often covered in rocky residue, irregular in shape, sometimes almost opaque. Once it is mined, the stone goes to a factory, where a kind of magical transformation unfolds. First, the crystals are cleaned, occasionally by hand, and occasionally in massive tumblers that literally scrub away the dirt. Then each stone is sorted by quality. Here is the interesting part. Only about 10% of all the amethysts unearthed are of jewelry-grade quality. The rest are used for more budget-friendly accessories or even ornamental items. The next step is cutting. This is a true art that merges careful science with the delicate touch of a skilled artisan. Picture a person peering through a loop, meticulously turning the stone to find the ideal angle. The most fascinating aspect? One slip of the hand can cause the crystal to crack. Let us suppose the stone is finished. The next issue is transportation. This task is not as straightforward as one might initially assume. Certain amethysts travel in specialized boxes, padded with foam inserts to protect them from the faintest jostles. In the case of geodes, they are often packed in wooden crates lined with soft materials. Uruguay has a distinctive export program for its amethysts. Stones are sold directly at auctions, drawing buyers from all over the globe. In Brazil, on the other hand, most of the output goes straight to large enterprises that handle both cutting and further distribution. The price of amethyst is determined by factors like color, clarity, and size. The most expensive pieces boast a vivid purple tone with a slight reddish shimmer, often called deep royal. Such stones are frequently utilized in luxurious jewelry, which can appear at international auctions. Here is something surprising. Even though technology has improved remarkably, a great deal in this field still hinges on human effort and observation. It is a tradition passed down through many generations. Even the extraction itself relies more on manual labor than on large machinery. Initially, after identifying a promising zone, preliminary work begins. If the amethyst is near the surface, excavators remove the topsoil, creating large open pits. In places like Minas Gerais and Bahia in Brazil, these open pits can span several dozen feet across. However, if the amethyst is buried deep, the operation goes underground. Mines that yield this crystal can extend about 320 feet into the earth, forming a vast maze of tunnels branching out in all directions. Breaking through the tough layers of rock is the first step to reaching amethyst. This may involve using explosives or drill rigs, but it is not as dramatic as one might imagine. It must be done very carefully to avoid shattering the precious crystals. The people responsible for this work are genuine experts. They even live by an informal motto: it is better to go around than to destroy. A carelessly managed blast can reduce a stone to fragments. Once the deposit is exposed, miners proceed by hand or with small tools to gently dislodge the crystals. Envision the scene: darkness, illuminated only by the glow of headlamps, and silence broken by the occasional strike of a pickaxe or the hum of a handheld saw. Everything relies on the miner's dexterity. Even the most subtle motion can determine whether a crystal remains intact or breaks. Some refer to this phase as jewelry-level work. The amethysts that are found are typically surrounded by quartz rock and clay, so they are cleaned right there in the mine. This is painstaking work, removing layer after layer and taking care not to harm the delicate crystal structure. It is reminiscent of restoring an antique vase. The most valuable crystals are separated by hand, with every movement carefully planned. Interestingly, the ambience in these mines can be quite a spectacle. For example, in the famous Las Vegas mine in Uruguay, amethysts shimmer in the darkness under the beam of a lamp, creating the sense of stepping into a magical subterranean realm, radiating shades of purple and blue. In some locations, such as the Amethyst Park in Brazil, the mines are open to visitors, and people can witness firsthand how skilled workers gently extract the crystals from the walls. Those workers are the real heroes. They toil in challenging conditions. This is one of the most expensive and complex machines ever built by humankind. Constructing it costs more than $3 billion and takes over 7 years to complete. It can dive to depths of more than 3,000 feet, remain submerged for months without surfacing, and launch missiles capable of altering the course of war. But how exactly is a nuclear submarine, an engineering masterpiece that remains nearly invisible even to the most advanced radars, built? Right now, you are about to witness this incredible process. A nuclear submarine is a highly sophisticated engineering marvel, and its creation begins long before the first sheet of metal ever touches the manufacturing tools. The initial designs are developed using advanced computer modeling software. At this stage, several critical parameters are considered, including hull dimensions and shape, power systems, weaponry, and noise reduction technologies. The length can range from 300 to 550 feet, directly impacting the submarine's diving depth based on its class. The most advanced submarines can descend to depths of 2,000 or even 2,500 feet, while some experimental models can go beyond 3,000 feet. Based on these initial designs, physical models of the submarine are constructed and tested in water tunnels. This allows engineers to analyze how the hull shape affects maneuverability, water resistance, and noise levels. Meanwhile, computer simulations help predict the submarine's behavior underwater at different speeds and during various maneuvers. Once all simulations confirm the calculations, the blueprints are sent to production. This is where theory turns into practice. Building nuclear submarines requires special materials capable of withstanding extreme pressure at great depths while providing corrosion resistance. Typically, high-grade steel or titanium alloys are used. Steel is more cost-effective and easier to manufacture, as it can endure high pressure and impacts. Titanium, on the other hand, offers superior strength, corrosion resistance, and non-magnetic properties, which reduce the risk of detection. However, titanium is more challenging to process and weld, as its melting point is significantly higher, approximately 3,034 degrees Fahrenheit compared to steel's 2,500 degrees Fahrenheit. Before construction begins, all metal sheets undergo heat treatment, which involves heating, cooling, and applying special anti-corrosion coatings. The hull of a modern submarine is assembled from modular sections, simplifying the construction process. Metal sheets are cut with massive laser and plasma cutters, ensuring precision down to the millimeter. Each sheet is then shaped using hydraulic presses to achieve the desired curvature. Some parts of the hull feature spherical or cylindrical structures. The sections are assembled separately. These are massive rings, or compartments, that will be joined in the final stage. This modular approach allows different sections of the submarine to be worked on simultaneously, accelerating the overall construction timeline. Once all components are ready, the most critical phase begins: welding the hull. Welded seams must be exceptionally strong, as even a microscopic crack could lead to catastrophe at great depths. To meet all safety standards, automated electron beam welding is used, producing perfectly uniform seams. Additionally, every weld is inspected using ultrasonic scanners and X-rays. Most nuclear submarines feature a double hull design. The strong inner hull withstands deep sea pressure, while the outer hull provides a streamlined shape, improving hydrodynamics and reducing detectability. Ballast tanks are often located between these hulls, allowing for buoyancy control. To keep the submarine as stealthy as possible, anti-sonar coatings are applied. These include noise-dampening polymer tiles that absorb sound waves. microporous composite materials that minimize the submarine's acoustic signature, and noise-reducing coatings for the propellers and power systems. Once all sections are ready, they are connected. Gigantic cranes transport the compartments into specialized docks, where they are bolted and welded together. The completed hull is then tested for airtightness by filling it with compressed air and checking for leaks. A structural integrity test is also conducted in a hydrostatic pressure chamber, simulating real deep-sea conditions. Once the submarine's hull is assembled and its strength verified, it is time to install its most crucial component, the nuclear reactor. This is the heart of the submarine, allowing it to stay submerged for months, or in some cases, even years. A nuclear reactor is more than just a machine. It is an entire energy system consisting of various auxiliary components that occupy a significant portion of the submarine. Modern nuclear submarines use reactors that function by heating water to generate steam. The nuclear fuel, typically enriched uranium-235 or uranium-238, is placed inside the reactor's core. As nuclear reactions occur, heat is produced, which then heats water in a closed-loop system. The resulting steam drives turbines that generate electricity and power the propeller. The reactor is transported in protective containers and installed using cranes through a designated hatch on the upper part of the hull. It is placed within a specialized compartment in the submarine's core, surrounded by radiation-blocking materials. This compartment is also equipped with emergency cooling systems and reinforced safety barriers. The reactor is mounted on a shock-absorbing platform that minimizes vibrations and impacts during submarine movement. Next, heat exchangers and steam generators are installed to ensure efficient coolant circulation, followed by the installation of turbines and electric generators, critical components for the submarine's overall operation. Finally, the compartment is sealed with multi-layered lead and composite panels to minimize radiation exposure to the crew. To ensure functionality, an initial test ignition of the reactor is performed. During this test, power levels are gradually increased, radiation levels in all compartments are measured, and cooling systems are tested under maximum loads. With the reactor in place, the submarine is still far from operational. At this point, it consists of empty corridors and compartments, so the next step involves installing control systems, life support mechanisms, weaponry, and crew quarters. Sonar systems are mounted in the bow and along the hull, enabling the detection of enemy vessels and underwater terrain mapping. The onboard computer system and automated combat control stations are integrated, ensuring precise maneuvering capabilities. Weapon systems are also installed. Torpedo tubes are positioned at the front, equipped with automated reload mechanisms for rapid firing. Strategic submarines are fitted with missile launch silos located in the central hull. Each silo is equipped with hydraulic locks and pressure control systems, allowing for missile launches at extreme depths. Considering that the crew can remain submerged for months without surfacing, nuclear submarines must be self-sufficient. They are equipped with oxygen generators, carbon dioxide removal systems, heating and ventilation mechanisms, and water reserves. Ever seen those tiny capsule hotels? Well, submarines have something very similar: sleeping capsules. They also feature dining areas stocked with provisions and a command center filled with control panels, maps, and communication devices. After the living quarters are fully equipped, the submarine is almost ready for deployment. But the most thrilling phase remains: a series of rigorous tests to prove that it can withstand immense pressure, stay undetectable, maneuver in extreme conditions, and perform combat missions. These tests can last anywhere from 6 months to 2 years, and include both factory trials and combat training for the crew. The submarine undergoes another airtightness test, followed by assessments of its electrical and navigation systems, and a final reactor ignition. For the first time, the submarine leaves the shipyard and enters open waters. Stabilizers, hydraulic cylinders, and steering mechanisms are tested. Sharp turns, dives, emergency maneuvers, and maximum speed tests, typically 25 or 35 knots, are performed. The submarine then submerges to periscope depth, about 65 feet, to evaluate stability. At greater depths, ballast tanks are tested under load, and the submarine is gradually lowered to its maximum allowable depth, usually around 2,000 feet, depending on its class. Reactor performance under maximum load is also assessed. Once the submarine has proven its seaworthiness, combat systems are tested. Initial shots are fired using training torpedoes without warheads. Strategic submarines conduct the launch of a single ballistic missile, typically following a launch-dive-airburst trajectory. Tactical submarines perform test launches of Tomahawk missiles or similar weapons. The submarine also enters an area with hydroacoustic sensors, where specialists measure noise levels at various speeds and evaluate the effectiveness of its sound-absorbing rubber coating. Finally, the submarine undergoes a simulated combat mission, during which the crew must demonstrate full operational readiness,